From A-level chemistry, we learned that the product concentration time graph of a second-order chemical reaction is exponential, yet we were never taught the equation of this curve. However, with A-level further maths knowledge, this equation can be derived. Let's take a look at a simple case of a first-order reaction. Reactant A turns into product B at a rate constant K. According to the definition of the rate constant, the rate of formation of B is equal to Ka, and the rate of consumption of A is negative Ka. Currently, we are trying to find the relation between B and T, but the differential equation only contains A, which we want to eliminate. To do this, we need to express A in terms of B, and one way is by adding the two differentials. According to the sum rule, the derivative of the sum of two functions is equal to the sum of the derivatives of the functions separately. Thus, the rate of change of A plus B is equivalent to the sum of the rate of change of A and B. By substituting these derivatives into the equation, we find that the rate of change of A plus B is in fact 0. If we integrate both sides, we get A plus B equals A naught, where A naught is the initial concentration of the reactant. By subtracting B from both sides, we can express A in terms of B and substitute this value into the first differential equation. Without irrelevant variables, we can solve this differential equation by separating the variables and integrating them separately, ending up with negative ln A naught minus B equal KT plus C. Assuming there is no product formed at t equals 0, we can substitute t equals 0 and b equals 0 into the equation to find the value of C. Substituting this value back into the equation and exponentiating both sides gives A naught minus B equal A naught times t to the power of negative KT. Rearranging the equation gives B equal A naught minus A naught times e to the power of negative KT. This equation makes sense because at t equals 0, B also equals 0, which is consistent with our assumption that there is no product at t equals 0. When time approaches infinity, the concentration of B equals the initial concentration A naught, since 1 mole of A forms 1 mole of B. Thus, the terminal concentration of product B equals the initial reactant concentration A naught. Now let's look at second-order reactions. Assuming reactants A and B combine to form C at a rate constant K. You can pause this video here and try to figure it out on your own. Starting again with the definition of the rate constant, the rate of formation of C is equal to KAB, and the rate of consumption of A is negative KAB. The sum rule tells us that the sum of the rates is 0. I only showed A and C, but this equation works the same with B and C. So we have two equations, A plus C equal A naught and B plus C equal B naught, where A naught and B naught are initial concentrations of the reactants. Similar to what we've done previously, rearrange the equations to express A and B in terms of C, and substitute these back to the initial rate equation relative to C. We get a differential equation, which we then separate and integrate. The fraction on the left is difficult to integrate in its current form, so we express it in partial fractions. Assuming that you're familiar with this method, I'll directly display the result. Here I am assuming that B naught is larger than A naught. Substituting this result back into the integral gives us an expression that is easy to integrate. By using the quotient rule for logarithms, the expression on the left can be rewritten into 1 logarithm. Assuming that there is no product formed at t equals 0, we obtain the value of the constant C. Substituting this back into the equation, we are now 1 step away from obtaining the expression, and the final step is to make C the subject of the equation. First, multiply both sides by the denominator, then exponentiate the equation, and finally extract the logarithm from the exponent on the right. Next, multiply both sides by A naught minus C and rearrange the equation to move all the C terms to one side. Finally, we extract C by factoring it out and dividing each side by its multiple. To get rid of the fraction in the denominator, we multiply both parts of the fraction by A naught, which leads us to the resulting expression. By multiplying the denominator and numerator by -1, we can get this expression, which is the same as before, but with positive terms for both the numerator and denominator. Thank you for watching. This video was inspired by an online article written by Jeffrey Chasnoff, which demonstrates various applications of differential equations. I've included the source in the description. Please check it out if you find this video interesting.